Hi everyone, my name is James Powell.
Hi, James.
I'm going to try that again. Hi everyone, my name is James Powell.
Hi, James.
Howdy. We're at PyData Dallas. It's Saturday, April 25th. Some of you who know me already know about these details, but if you are interested in this talk or the kind of stuff that I talk about, you can follow me at Don't Use This Code on Twitter. You can email me at james@don'tusethiscode.com. And I'm in the process of resurrecting my blog at seriously.don'tusethiscode.com. There's a lot of puns to be made with that domain name. Those of you who knew about the call and response may know of me from NYC Python. So I run NYC Python. It's the world's largest and most active Python meetup group. We have a humongous data science community in New York, and we have events every Tuesday, study groups on Saturdays and Sundays, and big headline events for 100 people every other Thursday. So if any of y'all find yourself in New York City, come by the meetup group. We'd love to have you there. In addition to that, I work with NumFocus, and I help. So for those of you who don't know what NumFocus is, it's a 501c3 that funds projects like Julia, IPython Notebook. We provide funding for projects like NumPy, SciPy, SymPy, and so on. And we help put on conferences like PyData. So in addition to PyData Dallas, the next big PyData event that's coming up is PyData Seattle, July 24th to 26th. I hope you're already excited about being here today, and you're even more excited about attending your next PyData event. In addition to those two things, I help organize the Open Data Science Conference. This is a conference that's being held in Boston on May 30th and 31st. It's designed for users of R, Python, and Julia across the language spectrum, all data scientists, machine learning. It's going to be a really big event. Over 1,000 people will be there. A lot of really good speakers from the Python community, from the R community, from the Hadoop community, and from the Julia community. So typically, I speak on topics related to Python, software engineering, applications to quant finance, data science, machine learning. In fact, I gave an abridged version of this talk just yesterday at a conference about R, where I talked about three things that an audience interested in statistics in R don't care about: Python, software engineering, and then the third topic, which you'll see. That's actually supposed to be a joke. And no, data scientists don't really care about programming. I'm just going to say it here. They don't. But in addition to that, I've given talks this year at Tennessee. I gave a lightning talk at PyCon in Montreal. I spoke at the RStats conference yesterday. I'm here speaking at PyData Dallas. I hope to see some of you at some future events. I know I actually recognize some faces from events that I've spoken at in the past. So I hope to see some of you at Open Data Science Conference, PyData London maybe, PyData Seattle. It's actually going to scroll off the bottom of the screen. PyGotham. I heard today that PyTexas has announced. I've spoken there 3 years in a row. It's a really awesome event in College Station, so check that out. And PyData New York, which will be coming in the fall.
What's PyGotham?
PyGotham is New York's Python conference. We held it. It was held in 2011, 2012, and then we held it again in 2000. Holding it in 2015. It's a big event for people in the Python community, web programmers, data scientists, and system Python programmers. And a lot of really good talks. Last year we had Hillary Mason and Brandon Rhodes keynoting. It's a really awesome event. So I've spoken at a couple of PyData events, and you're going to see a little bit of a theme in terms of the topics I talked about. The very first PyData I ever attended and spoke at was PyData New York in 2012. After that, I spoke on generators at PyData Silicon Valley 2013. Which I followed up with 3 talks in PyData Boston on NumPy, embeddings of Python, and again, generators in 2013. Then I spoke about generators again at PyData New York in 2013. And then in 2014, I decided, generators have another year's worth of life to them, so I spoke about that at the London event. And then I said, well, Silicon Valley hasn't heard this talk yet, so I changed the title a little bit, rewrote the materials, added some new stuff into it, and I gave that talk. And then I said, the Berlin crowd probably hasn't heard this yet, so we did that in Berlin. And then in New York, I said, got to bring it back home. I'm from Texas originally, but I live in New York. So I thought, bring it back home. So I gave that talk there. The talk I'm giving to you today is my 9th PyData appearance, and it is called Integration with the Vernacular. And it is not a talk about generators. So if you do want to know about generators, you can probably look me up online. I've given a lot of talks about that stuff. It's a really, really interesting topic. And I noticed that those talks were going in a certain direction, further away from something related to the computer science behind that and just an enumeration of features, and towards something closer to what you might think of as software engineering, where the engineering is a main part of it. So the subtitle for this talk is the NumPy approach, but the contents of this talk is more about engineering. And I know this talk may, in some cases, belabor some mathematical analogies. I'm trying very hard to make this talk as clear as possible and to present this material in as pure a fashion as possible related to engineering as a discipline unto itself, separate from computer science, separate from anything else. I mean, engineering, in my mind, is a human process that is related to the deliverance of some artifact that happens to be software, subordinate to some higher objective, some business purpose. And I think there's a lot of interesting content around what it means to write software, what it means for software to evolve, for requirements to evolve, some of the modeling problems there that are distinct from even what you might talk about in computer science or even what you might talk about in what passes for software engineering these days. That said, this talk is about creating kind of a language and a set of conceptualizations around software development, a common way, a framework for us to discuss common problems. And the purpose of this talk is to propose maybe some pieces of a framework, some pieces of a dialogue or discussion around how NumPy is used and how it situates itself in software. So one example of that, and one thing that I can think, a very rough statement that we could make, is that, and unfortunately to belabor a mathematical analogy, in the process of writing code, what we're doing is we're doing something akin to constructing an algebra. We have some domain, some well-defined domain of objects, that's our input data. Then we have some operations that can be performed on that. Those are the functions that we write. And we assert certain properties of those, and we may even directly test them, which is something that you wouldn't do in a purely mathematical context. You wouldn't ever write a unit test for a mathematical theorem, but in our field we do that. And then you take this construct, this algebra, and you subject it to inputs you've never seen before, and you say, because it's well constructed, because it's well defined, and because I've demonstrated certain characteristics, I've demonstrated that properties hold in a certain way, then I can accept arbitrary input data, and I can say that these properties still hold on the output data, that these properties still hold on this algebra. I will warn you that this talk has been constructed to be as inscrutable as possible. So with that said, let's start with a little bit of classical Chinese history. So, in 1919 in Beijing, there was a socio-political and cultural movement called the May 4th movement. It was started by a bunch of students and a bunch of academics, and there were a couple of authors who were very closely associated with this movement. There are a couple of names that, if you're familiar with, I would say, pre-contemporary modern Chinese literature, you may know Lu Xun, Mao Dun, Lao Se. And they're all typified by this anti-imperialist, this very liberal approach to how they wrote. And there was one interesting characteristic that was introduced with the May 4th movement, which was the use of vernacular Chinese for writing, the introduction of a written, literary vernacular Chinese. Prior to this point, prior to 1919, all written Chinese was in classical. So you can imagine up to 1919, if in the English language we all wrote using Shakespearean English. And that was the situation. And with the May 4th movement, this was reformed. The use of a common language, the use of the actual spoken language as a written form was introduced. And when we talk about things like classical Chinese or literary Chinese, one element that typifies these is the existence of Chenyu, which are 4-character proverbs. They are set phrases which have a specific idiomatic meaning that are usually derived from some classical text. If you think about ancient Chinese, if you think about Chinese historiography or classical Chinese education, it's modeled around typically an appreciation of the classics, sometimes even memorization of old texts. And so there are always these fixed phrases that pop out that get integrated into the language as a whole. One example of them that's a fairly common Chenyu is falling leaves return to the root. And this is usually used to describe, for example, how as people age, they want to return to their ancestral homes. And if we take a look at this phrase, we can actually try and determine where it came from. We can see it appear in everyday conversation. There's even a song by this title. But if you look it up and you try and figure out where this came from, you go in your dictionary, you'll see that it comes from an old Buddhist text called the Records of the Transmission of the Lamp. And if you actually look up that text, you'll find that it's actually part of a dialogue between a master and a student. And the student asks the master some question. The master responds with this very pithy phrase that leaves return to the root. And if we think about an analogous situation in English, we can see that Shakespeare himself spawned quite a bit of what we take to be common, everyday, average English. So if you look at, for example, the titles of books, the titles of movies, the titles of dramas, you can see a lot of Shakespearean terms pop up. North by Northwest was actually something that came from Shakespeare. What Dreams May Come is from Shakespeare. Murder Most Foul is from Shakespeare. Star Trek VI, The Undiscovered Country, is from Shakespeare, minus the Star Trek VI part. And you can see with the situation of even this 4-character proverb, there is some attempt to make it more naturalistic. So if I were to say murder most foul, that might pop out to you as something that is poorly integrated. It sounds a little bit foreign. You might say that must be an allusion to something. And in the case of this 4-character proverb, falling leaves return to the root, 叶落归根, you can see that in the modern iteration of it, they swap the first 2 characters, because in the historical iteration, it's supposed to be what the first 2 characters swap, 落叶归根, and actually I think it's supposed to be the other way around. But what you can see is an attempt to take this classical phrase and some ways that it evolves alongside the modern language in order to be a little bit better integrated. But still, if you're reading a text, this will pop out to you as something very unusual. In fact, we have the same situation in English, except these terms have been so thoroughly integrated into our language that we don't notice them at all. So foregone conclusion is from Othello. If you ever say foregone conclusion, it's not something that existed in English. It's not some phrase that was just constructed. It's a set phrase that we're absorbing from a literary text. Similarly, sea change. Sea change has meaning in terms of the allusion that's being made to the Tempest. Send packing is actually from Henry IV. So all of these phrases that you might assume are very common colloquial English are actually extracted from these literary texts. And this is the situation that you have in classical Chinese, and even in modern Chinese as well. An example of that might be a very simple phrase in Chinese that a proposal is not guaranteed to go through. And if we break this up into parts, you can see guaranteed here actually has a 4-character phrase right in here. And this 4-character phrase is being used in an adverbial sense. We're trying to modify that the proposal is not trying to go through. And if we look at that adverbial phrase, there's no way for us to split that up. It's just one set phrase that's transmitted to us from some ancient text. If we actually look up this phrase, we can see it was transmitted to us from a very ancient text from the Sui dynasty, so hundreds of years back. And in the original form, it doesn't even come out as the modern form. But we have this phrase where you're reading a sentence, and the sentence is written in a vernacular form, but there are parts of the language that just don't really integrate. They just pop out at you. But it's something that's very commonly done because these phrases have very rich meaning in a very compressed form. So this is, I think, an analogy to the way that NumPy code ends up looking. And it's a little stretch, but I'll show you. It really is. Okay. But, so we actually have this. So, what is NumPy? NumPy is your library for scientific and numeric computing. It's closely related to SciPy. Libraries that you might use like pandas are built on top of it, as are other libraries like scikit-learn. And if you think about what NumPy really is, you might start by looking at the NumPy documentation and see that inside NumPy you have a submodule called linear algebra, and you have a function called inverse. And you might look a little bit closer and you say, oh, you have an FFT, and you might say it's a collection of functions that allow you to deal with data in a mathematical numeric sense. But I think fundamentally, NumPy really comes down to the data structure that it provides. And even if you look at the documentation, 90% of it is dedicated to describing operations and characteristics of this data structure, namely the NumPy ND array. And the NumPy ND array gives you some mechanism for performing broadcast calculations. So you can see when I multiply times 10, every element gets multiplied times 10. I can do things like indexing, so I can take that NumPy array and I can index to remove all the elements that are greater than 5. And when I look at the NumPy array closely, I can see that it's been specialized, and it's been specialized on a type. And this is something that is already very different to what we consider in Python. In Python, lists are basic collection type that we're encouraged to use as thoroughly as possible. The list is not specialized on any type. The contents of it can be heterogeneous. And if it were specialized on a type, it certainly wouldn't be specialized on a type like an int64, because we have no notion of machine types in Python. We have this very beautiful system in Python 3 where you go from ints to longs to floats seamlessly. Although getting back to ints is another deal. So what you can think of for NumPy is NumPy kind of provides us with something like a constrained computation environment. It provides us with an environment where we are forced to define certain things. We're forced to provide the computer information regarding the types that we're using and the operations that could be performed on those types. We tell NumPy, here's an array, and it contains int64s, and what that represents is up to us. But by giving NumPy that information, NumPy can then go behind the scenes and specialize certain code paths given the information that you provided it. Namely, that you're dealing with int64s, so instead of having to go through this very long dynamic dispatch chain that you'd have to go through in Python if you were taking a list and mapping multiplication by 10 across every element, you'd have to go through your PyObject multiply, and then you'd have to dispatch to some PyNumber method, and you'd have to dispatch to some method implemented on the actual type object itself. NumPy says, well, I have an int64, let me emit a machine language instruction, or let me get as close to that as possible. There are certain implicit guarantees or certain implicit information you're providing the machine. For example, if you had a list of Python objects and you wanted to multiply every object by 10, whatever that might mean for that object, those Python objects could encode or could include any arbitrary code behind this multiplication call. And so there could be interdependencies between those pieces of data. In fact, you could have references, and so multiplying one element by 10 in place might have some meaning, such that if you multiply them in parallel, you'd have some race hazard because you're actually multiplying the same entity twice. NumPy forces you to deal with machine types, and it forces you to deal with this array type. And those are types which cannot have these interdependencies. So by putting your data into a NumPy array, the NumPy array could presumably, given some broadcast operation, give you an optimal implementation of it that did everything in parallel using threads, cores, using whatever multiprocessing mechanism you want, whatever concurrency mechanism you want. And that should be something that NumPy could do in some guaranteed fashion because you've given enough information to make those specializations, to make those optimizations, and in a sense that Python cannot. And so what you'll see is that for a lot of code, you'll have this very free-form Python layer where pretty much anything goes. It's completely dynamic. And then you'll drop into this very restricted computation domain where everything's defined at the level of what you need in order to get performance from the machine, where the operations are very well defined. Multiplication means float multiplication or integer multiplication and nothing else. Addition means the same thing, whereas in Python, addition can mean anything of a number, can have any of a number of meanings, right? Addition in Python doesn't have to be associative, doesn't have to be commutative, because you can implement it in any fashion. The path library allows you to add paths together to append them, right? It allows you to divide strings to create paths. And that has no meaning at all in a numeric domain. But with NumPy, you're sufficiently constraining what you're looking at such that everything can be done in a fast and effective fashion. So I'll give you an example of what the NumPy approach looks like. Here we have just some dummy data representing dates and closes and volumes. And we can do something like calculate a volume-weighted average price. And NumPy provides these high-level building blocks for doing that. To do a volume-weighted average price, you would just use a function in NumPy called average and pass it a keyword argument called weights. And then NumPy behind the scenes would be free to implement this in whatever fashion it wanted. Similarly, if you want to do exponential moving average, in NumPy, you might take a function that gives you an exponentiation of every element in a NumPy array. You take a linear space from -1 to 0 with a certain number of samples representing the window that you wanted. And then you take that and convolve it against the original data signal. Because as we know, convolution of a square wave with anything else is a moving average, right? And you can see this NumPy approach is about taking these very high-level building blocks and combining them to form computations. And you could think that in the context of an actual software application, you might have some code that reads data in, some code that does manipulations, some code that takes user input, and then at some point in the application, you drop into a very restrained computation domain where you could perform these computations, and you could be guaranteed that they're performed effectively. One thing that you can do with this approach, and one thing that even the generator approach makes very amenable, is that you can start to model your computation in these high-level building blocks, and then your story for performance is that when you have identified that certain computations are needing a little bit more, you can re-implement them as a building block at some other layer, in C, or in Python, or in assembly directly if you wanted to. And because you'd have something that looks like this, just convolving a kernel in this fashion, you could do that. So one question or one complaint that comes up sometimes is, if you're multiplying two matrices, it really matters what kind of matrices they are, right? If they're upper triangular, lower triangular, positive, definite, it may matter what the contents are in order to perform the most optimized evaluation. And NumPy may not have information about the actual contents of the data. Well, if you were to construct your computation in terms of these very high-level large building blocks, you could always, as a choice, take one of those building blocks and recode it in C or Python to include certain optimizations based on your knowledge of the underlying data. And NumPy allows you, or it encourages you, to structure your code in such a way as to make these very easy to do. So NumPy can be used. So one example of that might be this. This is my favorite NumPy example. It's a great teaching example because it shows off a lot of the different parts of NumPy. This is an implementation of Newton's method for finding square roots. So when you use Newton's method, you take a function where you want to find the zeros of it. You take its derivative, and your subsequent guesses are determined by the previous guess minus the function evaluated at some point divided by the derivative of the function evaluated at some point. And so here you can see I built this building block called step that just takes some target, given some function, takes some target and some guesses, and then gives you a single step and yields each step as you go. And in each step, I just determine which of the elements are unsolved, and then I perform this very nice broadcasted operation where I evaluate the next guesses and only mutate the elements of my set of guess for those that are outside of the threshold. And then for implementation, I can end up with this nice little looking visual here, where you can see I'm trying to calculate the square root of these 10 numbers, and you can see over the number of steps how quickly it converges. And you can see this is very nice and very common for Newton's method. We can see it's a fairly fast convergence out to 6 decimal places. And this is a typical type of way that you might use NumPy. And you could say if this weren't performant enough, or if I had certain extra assumptions that I want to make about the data, then I'd maybe first swap out small pieces of this. I might swap out some of the underlying calls, like unsolved, in order to figure out which of these are unsolved. Or I might then, at some point, swap out the entire function. NumPy makes this very easy to do. Now, you might look at this and say that's kind of an obvious approach for writing code. But I don't think it is. And I think that you can see other approaches that are very distinct from this restricted computation environment approach. And one of the common ones that comes up is when you're talking about graph computing. And it seems like there is this push towards these integrated graph computing environments where computation is thoroughly integrated into the application itself. So an example of it is, say you have a financial example. Say you have a portfolio, and you want to value the portfolio. So this approach would say, OK, you take a portfolio class, and you notate some function as being a node in a graph computation. And in this case, for a portfolio, it would be summing the value of each of the positions for every position in the portfolio. And then for the position, you'd have a function that says, OK, the value of a position is its size times its price. And then if that position happened to be a bond, you'd say the price is a dirty price. And then the dirty price would say, well, I'm the clean price plus the accrual. And if I'm an amortizing bond, you'd have some additional logic there. If you're a CDS, you might say, well, I'm the present value of all the cash flows, and so on. And you could think, if you were to construct this graph, then if you were to change one small detail, such as the recovery rate for some common issuer, then you could effectively and efficiently recompute the entire value of the portfolio without having to do unnecessary computations. That's the premise of at least graph computing. But in this particular approach for graph computing, what you'll see is that you're encouraged to write the computational pieces alongside a lot of what you might consider the business logic or application-specific pieces. So you'd have your bond class both providing the computation of its price and its dirty price, but also providing things like its registration type, different regulatory or legal details, other details that might be used for data feeds or for other parts of the system. And in this sense, you can see that the computation, the raw piece of information that you want to compute, is being smeared throughout the application in a lot of different places. And you're not taking this approach where you have just a very confined computation domain, where you have free-form Python code that's manipulating these objects, and then it drops down into a restricted domain in which it performs a computation and then comes right back out. Now, the downside of this approach is that you can see that NumPy doesn't really integrate into the Python of today. NumPy is, to be fair, NumPy was written for the Python of yesterday. It was written many years ago, and the API that it provides is one that is amenable to Python as it existed at the time. But in some cases, you can see NumPy does kind of chafe at the edges. And there's some very simple examples of it. If you read through any introductory Python tutorial, they'll say, if you have a collection and you want to determine if the collection has elements or not, you'll do something like if XS, and that's the most idiomatic way to write it in Python. And then you'll try it in a NumPy ND array, and it'll blow up on you, because it'll try and broadcast that true-falseness. And it'll say, well, this is ambiguous. You need to say whether any element or all the elements are true or false. And so the response would be, well, if you wanted to write code to determine if a NumPy array was empty or not, you'd have to use len XS. And if you were to show this code to somebody who only did Python, didn't do any NumPy programming, didn't ever touch pandas, they'd look at it and they say, this is not idiomatic. They'd say, this is not how you're supposed to write it in Python. And so what that says is, when you write code that uses NumPy, you have to be aware that you're doing things in a specific NumPy fashion. In fact, we can see in a lot of cases some more recent features of Python begin to integrate not as well into Python, into this NumPy approach. So for example, one of the neat new features of Python is generators. They were introduced a couple of years ago. I've given about 30 million talks on generators. And it's a really interesting topic, and they allow for a lot of interesting ways for modeling problems. But you can see if we do something very simple, like we take a generator that gives you the numbers in a Fibonacci sequence, and we pass it to a NumPy ND array, we end up with this garbage. This is almost certainly not what you want. Now, to be charitable, you could argue that passing a generator to a NumPy ND array has some ambiguous semantics. It may or may not be clear whether you want the generator object or you want it to consume the iterable. And there may be some corner cases around choosing one or the other. What this does demonstrate, however, is that you can see a clash between different approaches, because you probably would not expect this result. And in a lot of cases, use of Python and NumPy gives you that result. So I'll give you a very short case study. I'm running out of time, but I'll give you a very short case study of some evolutionary programming. And this is when when I was working through this simple example, I started to realize that there was something very particular about writing code the NumPy fashion. So let's say that we're doing some basic evolutionary programming. The only things that we want are fitness proportional selection, one-point crossover, and bit flip mutation, and nothing more. So we'll start with something very basic. We'll start with a chromosome where it has either ones or zeros, and its fitness is based on the number of ones it has. So our fitness function would look something like this. And we might say, OK, we want to generate some random chromosomes to just test how this evolution algorithm works. So we may want to test it on different population sizes, on different lengths of the chromosome. We might want to graph it and see how quickly it converges. We might want to look at some of those characteristics. So we'll start with something that might look very nice to a pure Python programmer. You write a function called random chromosome. It's actually a generator, and it just spits out random values or random chromosomes. And the reason it's a generator is because it can encode that state very nicely, so you don't have to use a big object. You can just encode any of the state of the randomness into the closure. So if you wanted to then do something like deterministic seeding of this, you could code that into it very, very nicely, very simply. And you can see we're using a NumPy ND array, and we're using pieces like choice from the random library, and we're creating just a NumPy ND array of a specific size. And then we might want to create some populations. So here we have two populations with 10 elements in each population, one population of size 5 and one population of size 10. And you can see we're beginning to kind of mix and match Python lists and NumPy ND arrays. And this is where we're going to run into trouble. We might want to do something like calculate fitness for all of them. And we can do that kind of easily. It's beginning to look a little bit ugly, but we can map our fitness function to everything, and it kind of works. And of course, it's going to be a little bit ugly no matter what, just because we have this structure of nested lists. But it's doable. And then we might want to write some function that calculates our probabilities. So what we do is we map fitnesses to everything. We calculate the total fitness. And then we divide the fitness of the individual chromosome by the total fitness. And that gives us our relative probability. And we might want to write this as a generator so that we could perhaps deal with populations of unknown size, or we could have some nice streaming to this. There's no need to, in this example, to eagerly compute the entire thing. And then we might implement our crossover. And our crossover would be something very simple. We'll use NumPy.append in order to append two ND arrays. And we'll just swap the order of them based on a 50-50 chance of either swapping or not swapping. For selection, we want to select two mates from the population. So we'll just calculate all the probabilities. Then we'll use NumPy.randomChoice with some weighting. And that would allow us to do fitness proportional selection. And we'll select two mates. We'll do this as a single function, because then we can map it across the population to select everything. And then mutation, similarly enough, we'll randomly calculate a position, and then we'll just do a single bit flip of the position and use append in order to append the parts together, as we would do in Python. In Python, with a list, we would do x up to the position plus a bit flip plus x to the end, and that would be considered very idiomatic Python. And then for breeding, this is the last thing. our code would end up looking fairly simple. We'll just get every parent. For the number of children we want, we'll generate a child by crossing the parents together. And then we'll do some random mutations based on the length of the child. So we'll do up to a certain number of mutations. Well, the problem is, when we take this code and we want to step through it, the code will actually look really simple. When we step through the population, when we want to do one stepping of one evolutionary step of this population, it'll end up looking very simple. And we could code it something like this. We have a population that we take in. We select the breeds from the breeding pairs from the population. We call this breed function, and we're done. The problem is, when we want to do this, when we want to write this code in such a fashion so as to maintain the entire history of the population, so that we could do things like identify how the fitness of the population changed over time, so we want historical information, where we want to do populations of different size simultaneously, we're going to end up with this combination of the use of NumPy ND arrays and Python lists. And it's going to be an absolute and total nightmare to write. I tried to fit this onto a slide so that you could look through it, and it was just horrible. It was horrendous. And the solution here would be you need to take everything, stick it into a high-dimensional NumPy ND array, and then just do these high-level operations. And every single one of these functions where you see a for loop would probably have to be rewritten to use broadcasting. And so the problem here is that in order to make this usable, in order to get the performance that you want out of it, you would have to rewrite all of this code. And this is an indication that sometimes this NumPy approach does not integrate very well with a very standard, naive Python approach. This is not a situation that's unique to NumPy, not a situation that's unique to Python. Because once I started to realize this, I remembered back when I was doing research as an undergraduate, and I remember there was once a researcher who was doing some signal analysis. And she'd written some code. She was a fantastic C++ and Java programmer, and she'd written some code in MATLAB to implement the signal analysis. It was mostly about multipath signals in a closed waveguide. And she wrote the code, and the simulation was just dreadfully slow. And somebody said, well, actually, if you want to get any performance out of MATLAB, you have to use this hidden sublanguage of MATLAB that's all the vectorized computations. You have to go and rewrite all of the code to get any of that performance out. And what we can see here is that, and I told you I'd bring it back, we have a situation with NumPy that's somewhat analogous to the situation in classical or in literary Chinese. We have a very effective restricted domain where we can convey a lot of information and get a lot done, but it always seems to integrate a little bit poorly with the vernacular. It's something that pops out at you. It's something that doesn't really flow with the rest of the code. It's something that you have to be very cognizant of. And if you were to see code written in this NumPy fashion, it would immediately pop out to you. There are assumptions that you would have to make in order to use it. It wouldn't be a seamless part of the Python language. So that's integration with the vernacular, the NumPy approach. We're at PyData Dallas, and I hope you enjoyed it. Thank you.
Any questions?
No?
No?
Peter.
So what is, to go do the math backwards, what is the literary equivalent of NumPy in this then?
Like simplified Chinese, maybe? I don't know. I think the analogy is already fairly strained. Hey, as long as it's not a generator talk, I'm ahead, right? I don't know. I thought. So the genesis of the talk was actually, when studying contemporary and modern Chinese literature, this is a phrase that came up a lot, that classical Chinese poorly integrates into the vernacular. And it's something that stuck with me. And when writing code using the NumPy approach, I started to feel the same thing, that this is an amazing tool that's very effective in practice, but it just doesn't seem to integrate that well into my Python code. In some cases, it has its own style to it. And in some cases, I need to rewrite things, or I need to write things specifically from the start in a NumPy approach and abandon some of my traditional, some of the more idiomatic approaches in Python to be effective.
Are you seeing any trends in the on finance space where you can use the same language end-to-end from prototyping to going to production while maintaining the same language and the same kind of vernacular?
So
or
that's,
do you always have to kind of prototype?
I think the thought is people say, oh yeah, I prototype in Python, then rewrite in something else. Oh, so the question is, in finance, do you see the use of one language end-to-end from prototyping to production? And I think that everybody always says, oh yeah, I prototype using Python and rewrite in this or that. in finance, nobody rewrites the code. So if they're honestly, if they're prototyping language, it's probably the language that's staying around for a while. And it does seem like Python is one of these languages. In fact, at PyCon, I was speaking to one of the core developers who'd been in Python for a very long time. And he developed Python concurrent to him working as a commodities trader back in, I think, the mid-90s. So Python's use in finance is something that's been around for a very long time. I think it's still considered to be an emerging language, at least at this very large platform scale. We all know about Bank of America's Quartz platform and JP's Athena platform. And I think in those cases you see there's Python as maybe a top-level language with some substrate languages like C or C++ scattered throughout.
Any other questions?
Sheila?
So, this is a little bit like almost an impedance mismatch.
Yes.
Between the idiomatic Python versus the sort of thinking that's there in NumPy. Is it so big of a bridge to cross that you couldn't make an API wrapper?
So I think that's what Pandas is trying to be, kind of a wrapper that gets you a little bit closer. But so this term impedance mismatch is a really good one.
Can you explain what that means?
So I paid more attention in the liberal arts classes I took than the engineering classes, so probably I couldn't do it off the top of my head. Well, what it means is when you're, so you have Z and you have you're measuring the impedance across,
I know.
I mean, you have to match two transmission lines. And
Yeah.
Maximum, you have to match their impedance, their resistance against maximum.
But I think that what you might see is, I don't know if you could write an API wrapper around NumPy to integrate it better into Python. Because, for example, think about this. When you use Python, you're very strongly encouraged to use all the built-in data types for everything. You're strongly encouraged to use a list or a dict wherever you can. And that's going to be fundamentally incompatible with using a NumPy ND array all over the place. Peter, do you have a suggestion?
Well, so I was going to answer, this is actually a very, very good question. Building APIs is a way that it separates, I talk about the fluidity and the agility of expression. Building APIs is like going through Google Translate, right? And you lose a lot of the flavor of the texture and things like that. And the other approach is to, actually, what James was saying, using like dicts and lists and stuff in Python, making those faster while being able to use NumPy stuff. That's exactly what the Numba compiler seeks to do, is to seek to basically smooth over that impedance mismatch, not by wrapping functionality up and making you get at it only from a few API endpoints, but actually making it so you can sort of transparently talk about all these things, and then we'll go figure out how to make it fast, right? And that part is, and doing that artfully is the challenge, not so much, a lot of people make that claim, but actually doing it in a way that you can be expressive, you can write little inner loops that are still very Python-y, very lists, generators, etc. But then when you call it with a big ol array, then it goes and does the big ol array compute on it as you've written, in NumPy intrinsics. Actually, one of the things that Travis, my co-founder, talks about is that ideally, what he'd like to do is see that basically re-implement all of NumPy in Python plus Numba. Like there's only some few core things you really need. The data structuring part of it is core to that. Python, historically I would say there's this embedding. I think this is, by the way, James, this is a fantastic talk.
Thank you.
I don't think it's obscure at all, but that's because I'm Chinese and also a Python hacker. It makes total sense to me.
So I got to one person in the audience. That's good.
But the thing is that, I would say that NumPy's integration in Python was sort of a marriage of convenience from the early stages. Like, if you look at the matrix object, it was like some people hacking around and like, you can just kind of do this by overloading under get item and set item. Looks like a matrix, but you could do that with Python. People try to do this with C++, and it just gets harder and harder. People can't really do this with Java because there's no operator overloading, right? And so Python just happens to be, the language happened to be amenable, open enough to have this marriage of convenience, and then that really took off, right? And we're trying to now cement kind of the future of that by making that not so much marriage of convenience, but actually a deliberate, thought out thing moving forward.
All right, thank you, James.
Oh,